All right, had another abrupt end to that last video, but that actually kind of works out because we had started working out this problem and we established that the rate in is going to be 0 pounds per minute, and we started working out the rate out, but I actually wanted to change the way I was approaching that. So what we're looking for here is the rate at which salt is leaving this tank when we're trying to come up with an expression for R out. And we think of that as a rate, pounds per gallon, right? In particular, I was starting with the amount of salt initially in the tank over the volume, or sorry, the amount of salt in the tank at a given time over the volume of that tank at a given time. But because we have a different rate at which fluid is entering the tank compared to fluid exiting the tank, the volume of that tank will be changing. It's not going to remain constant. So we actually need to think through that for a second. Notice that the rate at which fluid is entering the tank is 3 gallons per minute, and it's leaving at 2 gallons per minute. That means that the volume, if I can just call it dV dt, the volume of the tank is going to equal the rate in minus the rate out, which is equal to 1 gallon per minute. Okay? So if what this means is that if t minutes have gone by, then we will have 1 times t, or just t additional gallons introduced into this tank. And that's just of the solution, of the fluid in the tank, not just the salt. So we need to consider that when we're finding R out. Okay, what is R out? Well, R out is going to be the rate at which salt is leaving the tank, and that's going to equal the concentration of salt in the tank at time t. But what is that? That would be A of t, which is the amount of salt in the tank, I'm just going to call it A, over the volume of water in the tank at time t. And again, what we established down here is that if we start with 300 gallons, then after t minutes have passed, we're going to have an additional t gallons of water in that tank. So this is going to be A pounds over 300 plus t gallons of water at time t. And then what I need to do is multiply that by the rate at which fluid is leaving the tank. And it's leaving the tank at a rate of 2 gallons per minute. Okay? Multiplying these rates together, I get 2A over 300 plus t pounds per minute. Okay, so to get my final differential equation here for the amount of salt in the tank, or the rate at which salt in the tank is changing at time t, we have dA dt equals R in minus R out. That's equal to 0 minus 2A over 300 plus t, or just dA dt equals negative 2A over 300 plus t. Now there's an initial condition that we can also attach to this problem, because at time t equals 0, we're told that there's 50 pounds of salt in this tank. So we have A of 0 equals 50, making this an IVP that we could then find a unique solution to. Okay, so had to rework the R out part of this, but this is actually the differential equation we'd be looking at here. Okay, one last problem, and then we're going to wrap this section up. This ended up being 4 videos. It should not have been 4 videos, but that's technical difficulties, unfortunately. So this one is an example of that virology application that we looked at before. Suppose a student carrying a flu virus returns to an isolated campus of 1,000 students. Determine a differential equation for the number of people x of t who have contracted the virus if the rate at which the virus spreads is proportional to the number of interactions between people who have the flu and the number of students who have not been exposed yet. And we talked about this exact application. Find it here. Right here. Okay, we came up with a model for this. And our model was dx dt equals k, some unknown constant, xy. X being the number of people infected, Y being the number of people not yet infected. But then we looked at a special case where if we were dealing with a community, or in this case a campus, with a fixed number of people, N, then we end up with this special case of this. So keeping that in mind, it says up here that a student who has that flu virus returns to an isolated campus of 1,000 students. Now this is, depending on how you read this, there's two different possible answers here based on the number of students on campus. If this student returning to campus is counted among these 1,000, then there are 1,000 students total. If that student is an additional student to these 1,000 students, then you have 1,001 students. And this sentence alone doesn't make it super clear, but we're going to go with the first interpretation. This student is counted among these 1,000 here. Okay, so we've already talked through the logic for this model here, and really now all it amounts to is just plugging numbers in, and we'll have our differential equation. So there's not much to do here. But one thing I do want to point out, this n plus 1 here, that is not, we're not going to use the plus 1 in our example. Remember, the plus 1 is when you have a fixed number of people in a community, and then one more person is introduced. That's the carrier of the disease who's going to start spreading it. But like we said, that student is already counted among those 1,000 students. So instead of n plus 1, we're just going to use the n here, or 1,000 in our case. This one is very straightforward. dx dt is equal to k. We don't know that unknown constant, so we're just calling it k. X times n minus x, but n in this case is 1,000. 1,000 minus x. We also want to make this an IVP so that we could solve for a unique solution later on down the line. And the way that we read this, we're interpreting it as that the one student returning to campus is the only one with the flu. So at time t equals 0, when that student returns, there's only one student with that flu. And that's it. Okay, so this one was straightforward, using the work we already did and just plugging in a number. Okay, that's going to be it for 1.3.